Yeah, chapter 5. I love it, man. You guys ready? Antidifferentiation. Antidifferentiation. If you can't spell it, you're in trouble. I'm just kidding. Yeah, another word for it, by the way, and it's pretty clear what that might mean. Instead of doing a derivative, you're going to be doing an antiderivative. I mean, if I give you a function, watch this. If I give you a function, if I said take a derivative, you know how to take a derivative, I hope. But if I said do an antiderivative, then that means you're looking for the function whose derivative is sitting here, right? You're going backwards. You're looking for the function this is the derivative of somebody. Who's that somebody? So you're going backwards. You're trying to find, you're doing antiderivatives. This is pretty famous without any rules or anything. This is famous and familiar. I bet you can figure out who the function is. What is it? Yeah, x cubed. And look at this notation. Watch this. So right off the bat, I mean that's part of a new chapter, a new topic. We got new notation, new language. So right off the bat, if I've got a function called f of x and I say find his antiderivative, we denote it with this capital F. Now, so what if I said let's take the derivative of capital F? Then the derivative of capital F is this little f. Right? Boy, don't get confused here. I mean, we need a name for his antiderivative. When I call this a function, I could call it, oh boy. What if I would have walked in and talked like this? F prime of x is 3x squared. Then what would you call his antiderivative? By the way, it's x cubed, right? His antiderivative is x cubed. But if I labeled this f prime, then what would you label his antiderivative? F of x. I mean, right? If this is f prime. But if I label him f, then the notation is the guy above f is capital F. And capital F prime is f. It's not that confusing. I guess I should stop. But hang on, watch this. What is f prime? Well, now I'm doing a derivative. And what, 6x? Is that what you said? But what would be another name for that? If this is capital F prime, I guess this is capital F double prime. Okay. I mean, I don't. The concept is we're looking for the antiderivative. Another name for that, by the way, looks like a completely different name, is the process of finding that antiderivative or doing antidifferentiation. The process is also referred to as integration. So I might use both words. I mean, really, the truth is I use that word a lot. It's called integration. We integrate. We integrate this function, and we get this function. We integrate or find the antiderivative. Let's try another one. And here's the notation, by the way. Here's some more notation for you. So the notation, the integral notation is this. We use this symbol, and we try to integrate a function, and then we have this little dx here. This is the notation that says, I'm going to write this for you. It says, please integrate, please, actually, back when they invented this notation, back in the 1600s and 1500s, they probably didn't say please, but nowadays. Please integrate this function f of x. What does that mean? Integrate f of x means find his antiderivative. Right, thank you. When you integrate this function, you got to find his antiderivative. And by the way, this little dx out here on the end, I want to say set means with respect to x. I mean, that's kind of telling me that the variable of this problem is x. I mean, maybe that's obvious. We always have x as our variable. Well, not always. We could have a function of t, right? I could have a function of t, and then I'd have a little dt here. I mean, just this sort of tells me that the variable of integration is x. The variable is x. We're integrating with respect to x. Yeah, that's how you read this sentence. Please integrate f of x with respect to x. Please find his antiderivative with respect to x. Hey, you know, a few minutes ago we did one. I walked in here, I got a little crazy with all my notation here, but I asked you, what's the antiderivative of 3x squared? And you said x cubed. It was obvious, you kind of did it in your head. You know, could it be another answer? Do you think there could be another answer? I mean, is there any other antiderivatives of 3x squared? I mean, is there any other functions? If you took their derivative, you would get 3x squared. Or is that the only one? Oh, what about x cubed plus 2? Let's take his derivative. If you take his derivative, what do you get? 3x squared. Oh, what if you took, hang on, what if you did x cubed minus 171? What if you took his derivative?
3x squared.
3x squared. So the antiderivative of 3x squared is really not him or him or him. It's kind of, it could be all these. It could be all these. You with me? That's kind of new. I mean, that's new. When you do derivatives, the derivative of somebody is just the derivative. Now I'm doing an antiderivative and I get a lot of different answers. But all the different answers they're just kind of off by a constant. You see that? And that's due to the nature of the concept that the derivative of a constant is 0. So I guess the integration of a 0, hang on, the derivative of a constant is 0. So what's the integration of a 0? A constant, I guess. Some constant, any constant. So, technically, when you do this antiderivative, the answer is, the notation I tried to teach you here is that it's a capital F of x, but now I'm going to add this plus c. And we deal with, this is kind of a new concept, but we deal with this plus c. It's a constant, and I'm going to refer to it as an arbitrary constant. But it's part of our answer when we're doing these kind of antiderivatives. It's part of our answer. It could be any constant. The answer, when I say do his antiderivative, it could be x cubed, it could be x cubed plus 2, it could be x cubed minus, it could be x cubed plus any constant. By the way, it's plus or minus, so that we put plus c, but the constant could be positive or negative or 0, I guess. Okay, hang on. Please integrate f of x with respect to x. That's sort of what this says. And then the answer is, I'm going to say that the answer is I want to call this a family of functions. The answer is kind of this family of functions. And the answer is x cubed plus c. When I say, let's integrate 3x squared dx, the answer to this is, we've been doing it over here kind of, but the answer to this is, the antiderivative of 3x squared is x cubed plus c. And it's kind of a family of functions, you know, because how do you graph x cubed plus c? Well, I'll show you. If the c is a 0, then it's just good old x cubed. Right, you guys? But if the c is a 1, then it's x cubed plus 1, which looks like this. This cubic function pushed up 1. If the c is a 2, it's x cubed plus 2. If the c is a negative 7, it's x cubed minus 7. So this function plus an arbitrary c can be depicted as a family of functions. I mean, there's millions of these, or infinite amount of these curves, depending on what c is. Yes? Does that mean you have a question? Go ahead.
I was trying to tell you that I really want you to stop before I really start to get more confused than I already am.
I know.
Over there we have the integration symbol thing, and you have 3x squared dx equals x cubed plus c. What does that represent?
Right. So this symbol means please integrate this function with respect to x. And what does the word integrate mean? The word integrate means
Antidifferentiation.
find the antiderivative. So this says, please find the antiderivative of this function. Your main focus is on this function. The symbol here means let's integrate. And this symbol here is just sort of telling me that the variable is x. So this is part of the proper notation. And at the moment, don't be concerned with this notation. Just accept that it means please integrate or please find an antiderivative. So the focus should be on the function who you're finding the antiderivative is, and we've discussed how that's x cubed. I really haven't taught you how to do it, but we all know that. The antiderivative of 3x squared is x cubed. And now the new thing I'm teaching you is that we got this plus c. It comes attached to this. This is kind of a key chunk of notes right here. I mean, this is our new way of talking in chapter 5. And we'll adapt this and learn some more versions of this, actually. But this is us doing integration or doing antiderivatives. Let's do another one. So can you guys do the antiderivative? Here we go. Can you do can you do this? I'm sorry. Can you do this problem? And it's all brand new notation, except you have sat here for 10 minutes and learned what this notation is. 10 minutes ago, you didn't know what the hell was going on. But now you understand this notation. You understand, you're looking for the antiderivative. You're looking, it's back. If you know your derivative rules well, that's why hopefully we learned our derivative rules well. But if we learned our derivative rules well, we should be able to kind of go backwards and look for these antiderivatives. Does anybody know the answer to this one? Sine x. You think the answer is sine x? Now, should I mark you right or wrong?
Sine x plus c.
Oh, you better put your plus c. That's right. You better put your plus c. But good job. You did this integral. And you just, I mean, there wasn't much to it. You already kind of knew it. You knew your derivative rules, so now you're doing your antiderivative rules. Yes, Carlos?
Sine is not a sine, it's negative sine. Right.
Well, now we're going backwards. I'm sorry. But we are going backwards. So this, and I get confused with sine and cosine myself. Now, hang on. The derivative of sine, and so I do this. I sit here and do this little dance in my head. Look, it's like a little two-step dance. It ain't much of a dance. But the derivative of sine is the derivative of sine. The derivative of sine is cosine.
Yeah.
So if someone says integrate cosine, I'm back to no. I said integrate. So quiet a second. Listen to me a second. Derivative of sine. Please take the derivative of sine. Cosine. Now let's integrate cosine. Back to sine. When I say integrate, that's the opposite of doing a derivative. So we did good. The integration of cosine is sine. Yeah. The antiderivative of cosine is sine plus c. It's actually not just sine, but it could be a whole family of functions that has this derivative. You can always, you know what's cool about these antiderivatives and integration is you can check yourself. When you do one, after you do the answer, now check yourself by doing his derivative. Take his derivative and you get this, I hope. So you can check yourself. Yes, Carlos?
What exactly does that graph right there mean?
So, what I was trying to say, and maybe I'll just say it again with this picture, is that when you integrate, you get the antiderivative, which is a function. But when you have a function plus c, it's kind of not a function, it's kind of a family of functions. The answer, f of x plus c, is sort of a family of functions, depending on what c is. Now watch, I'll illustrate that again, Carlos, watch me. So I want to graph this answer. Well, it's a whole family of answers. Listen, if c is a 0, then it's just a sine function, which looks like this. So here's a picture of it when c is 0. If c is a 1, what is it? It's the sine function pushed up 1. So now it's this. What if c is 2? It's the sine function pushed up 2. So now it's this. What if c is a negative 1.74? Then it's pushed down negative 1.74, and it's a sine function. So if someone says graph your answer to an integral, your graph is a whole entire family of functions. We really don't do a lot of this. Okay, I'm just doing this as an illustration for what this answer is. It's not a single function in a way. It's a family of functions. And if someone gave me a certain piece of information, then maybe I can find the particular member of the family that they want. And so maybe sometimes we find this arbitrary c. For right now, I haven't done that yet. We just got an arbitrary c as part of our answer. But then there's some problems where you want to go a little further and find that c. Let's try to find that c according to, well, how about this? How about if I was looking for the one member of, this is a whole family of functions, but what if I was looking for the one member of the family that went through this point? Hey, what is that point? 0, 2. That means when x is 0, y is 2. Is that what that means? Okay. If I wanted to find that particular member of the family, I think I would go to this answer here, I would plug in a y value of 2. And I would plug in a 0. That would be the sine of 0 plus c. Are you guys following me? This answer is big old f of x. I can call that my y value. There's my x value. It's a whole family of functions when you got that plus c in there. But I'm adding this to the question now. Can you find the one member of the family that goes through this point? And that means when x is 0, y is 2. Well, yeah, you can. What that really means is when I say find that one member of the family, I'm really saying, can y'all find c? Given this condition, or this initial value, or this condition, or this requirement, or this piece of data, can you find c? And yes, we can. We can plug in that y and that x, and we can probably find c. Let's see, what is the sine of 0?
0.
Oh, 0. So if that's a 0 plus c, I guess c is 2. So the one particular member of the family that meets this requirement is this, sine x plus 2. When someone said integrate this, it was a whole family of functions. But when someone said, find the one member of the family that goes through this point, then I got a particular answer. Sort of a general answer with a plus c in there, and then sort of a particular answer. Yes, Carlos?
How did you get y equals sine x plus 2?
Yeah, you saw me, and you can go watch the video later. I said, let's try to go through this point. So I plugged in x equals 0 and y equals 2. Here's my y, here's my x. Y is 2, x is 0, and I found out c is 2. I I found C that made me meet this requirement.
Oh, you pointed back in for C. I didn't even see that.
Let's try this, you guys. Can you integrate this guy? Can you find his antiderivative? Let's try this one. Find his antiderivative. And by the way, what's funny is I haven't taught you any rules yet. All I've done is, well, tried to make you think backwards, right? But there's a whole bunch of rules. Hang on. What was the old power rule? When I say, you got to be careful in this. Now that we're in chapter 5, we're doing antiderivatives, but we still mention derivatives. So I do derivatives, I do antiderivatives. I do a little bit of both, and you got to get your mind organized for that. The big new topic is antiderivatives, but we do some derivatives in the process. We do some thinking. But anyway, watch this. Way back in the day, I gave you this rule, and it was called the power rule, and it's the derivative power rule, and it taught you how to do the derivative of x to a power, and you guys all know what it is. You bring the n, you multiply the n down front, and you subtract 1, right? That's the old power rule for derivatives. Well, now antiderivatives is doing this backwards. So we can make a rule for this. If you're trying to do a derivative of an antiderivative of x to the n, you're doing this power rule thing backwards. So wait a minute. What did we do? What was the rule? Multiply by n and then subtract 1. So I want to do the opposite of that. I want to do the opposite of that, and I want to do it in the opposite order. Hang on. So multiply by n and then subtract 1. So now I want to add 1 and then divide by that new power. Plus C. Here it is. This is the power rule. I tried to make, anyway. Tried to make you think about it, but then I couldn't help myself. I had to just tell you what it was. But it is these steps backwards. It's not a miracle. It's just this backwards. Multiply by n, subtract 1 was the power rule differentiation. Now I add 1 to the power and divide by that new power. It works. Let's try it on this. Here we go. If I want to integrate x squared, I use this cool new rule now, this power rule. I don't really try to think, what is the antiderivative? No, I just use the rule, man. Add 1, divide by, what do you get? X cubed over 3. By the way, there's some people say it like this, x cubed, when it's over 3, you divide by 3. Dividing by 3 is the same thing as multiplying by 1/3. So let's not argue with each other about that. I will talk like this sometimes. I will talk like this sometimes. They are the same. They are the same. So please accept both ways of talking. You guys okay? By the way, now let's check it. See, that's the thing. You can always check these. Take his derivative. Take his derivative. You bring the 3 down, it kills the 1/3, and you subtract 1, and you get x squared. Oh, and you go take the derivative of the c, and you get 0. So you get x squared. This is it. Hey, this is the power rule for antidifferentiation. It's the opposite of this power rule. Listen, you guys, this is your main rule. This is it. You know what? We have product rules and quotient rules and chain rules when we do derivatives. Guess what? We don't have those when we do integration. We don't have product rules. We don't have quotient rules. We don't have chain rules. We don't have those rules. What we got is, later in this chapter, we got to get creative and do some U substitution. We do some we do some cool stuff. But we don't do product rules, quotient rules, and chain rules. There is no product rules, quotient rules, chain rules for anti-differentiation? There is none. Really. Not really. In Cal 2 you learn some other fancy stuff, but not product rules, quotient rules, chain rules. There is none. So guess what? What I'm trying to say is this is kind of your main rule right here. So could you integrate this? Here it comes. So now here's one for you. Nope. Integrate this guy. All right. You guys try it. I'll be back in 1 minute. All right, I wonder how you did it. Any ideas? What do you want to do?
Divide by 4.
Maybe, maybe not. Hang on. Here's our rule. Okay, if this is the only dang rule you got, then how do you adapt? I mean, I don't feel like this rule works for him. This is an x. It is an x to the n, but it's an x to the n and sitting in a denominator. That's not the way my rule is. My rule is an x to the n sitting here and not in the denominator. So, I mean, I have to use the rule as it was given to me. Or I need to adapt this. I mean, you remember the game. When we did derivatives, we would rewrite this. We would move it up and then take a derivative. Well, that's what I got to do here. I got to move it up and then do an antiderivative. I got to make it look like my rule. My rule is x to the n. And I make it look like my rule by rewriting it, x to the negative 3 dx. Now, does it look like my rule? I mean, yeah, now it looks like x to the n. So now I do it. Add 1 to it, please. Add 1. X to the negative 2. Divide by negative 2 plus c. We're finished. Except maybe we could clean up that answer a little bit. But we just did this. We integrated this function. We found his antiderivative. There it is. And it's new and different than what you've been doing for a couple months. But you can handle it. It's just backwards. By the way, if you did want to clean up this answer, maybe I'd move this x to the negative 2 into the denominator. 1 over negative 2x squared. Does that make sense to you? Okay. What about this? Here's another one. Can you please integrate this function? Square root of x. I want the antiderivative of the square root of x. Okay, what kind of rule does he fit? Well, I only got one rule. This is the only rule you got, kind of so far. So what are you going to do? Perhaps you'll rewrite him so he looks like a power. Now he looks like a power. And then you'll add 1 to that. You'll add 1 to that. So the answer is x to the 3/2. When you add 1 to it, x to the 3/2 divided by 3/2 plus c. You guys okay? Simple? I mean, it's okay. It's new. I'm using this rule. I'm adding one and dividing. Listen, you'll probably never hear me say this again. When I say the phrase divide by 3/2, I kind of rather not divide by 3/2. Instead of dividing by 3/2, I can multiply by 2/3. So I'm dividing by 3/2, but that's the same as multiplying by 2/3. So I'll probably do that in the future. I mean, you add 1 to it and you divide by 3/2, but I stop myself before I divide by 3/2. I say, wait a minute, dividing by 3/2 is the same as multiplying by 2/3. Cool, there's my answer. You could check it. How do you check it? Do his derivative. If you do his derivative, you should end up right there. Let's just try. If you bring the 3/2 and multiply by the 2/3, I think you get 1, and then you subtract 1 and you get x to the half. Yeah, awesome. That's it. It works. Okay, we got this power rule. We got this rule. Check this out. Watch this rule. If you have a k times f of x dx, what you can do is write k times the integral of f of x dx. Or in other words, you could have k times capital F of x plus c. Now, what the hell did I just do? I mean, can you guys read math? What is this rule? This rule says if you have a multiplied constant, a constant multiplied by your function, that's what k is, a constant. If you have a multiplied constant, you are allowed to sort of pull it out front, go ahead and integrate, and then put the constant, multiplied constant back. It's pulled out front, and it's multiplied out front, and then you just put it back. That, guess what? We did that rule with derivatives. So it works with antiderivatives. You can just pull a multiplied constant out front, a multiplied constant out front. Here's another rule. What's the integral of f of x plus or minus g of x? See, I haven't been doing this. I've been integrating sort of one function, but what if you have two functions, added or subtracted? Well, guess what? I'm going to write capital F of x plus or minus capital G of x plus c. So what the hell did I just say? Maybe I should have wrote that a little better. Hang on. I'm going to write this differently. I'm sorry. I'm going to write the integral of f of x dx plus or minus the integral of g of x dx. And then the answer to that is capital F plus capital G plus or minus capital G plus C. Now, that's a rule, and it's an important rule. Do you understand it? What am I saying? I mean, sometimes these rules, you don't think they're rules, you think they're common sense. And maybe you do think this is common sense. It is kind of common sense, but it's also an important rule. I mean, what it says is if you have separate terms, added or subtracted separate terms, you're allowed to integrate each separate term. When you have separate terms separated by plus and minus signs, that's what terms are, separated by, you're allowed to integrate each term separately. Like two separate integrals, and then you get your two separate answers added together. That's all. If I didn't tell you that rule, you probably would have done that rule. Anyway. So here's what I'm saying. Look what I got going here now. Now that I've added those two rules, these are important rules, added to this rule here. Now, can you integrate this? 3x to the fourth minus 5x squared plus x minus 2 dx. I mean, you're integrating a big polynomial now. But according to what this last rule I just wrote down, I mean, how do you integrate a big polynomial? You just integrate each term. Thank you. You just integrate each term. And I don't really want to write that. I mean, I did it here. But I don't want to write, you're doing his integral, then you're going to do his integral. I mean, that is what you're going to do. Just to save myself some writing, I do it in, Jesus, what am I saying? I'm suggesting that you might be kind of, you're doing that integral, minus you're doing that integral, plus you're going to do that integral, minus you're going to do that integral. Are you guys with me? Now, listen, in the future, you'll never see me write all that out again. I'll just do it. And you probably don't want me to write it all out, but you just integrate each guy is what you do. But let me illustrate one other point. What do you do with this 3 sitting out front? See, you got a rule for x to the 4th. How do you do x to the 4th? How do you do x to the 4th? You got a rule for x to the 4th. Okay. Well, then what do you do with the stupid 3 sitting out front? It's a multiplied constant, multiplied 3. You just kind of pull it out front, which is this rule. This rule saying you can pull those multiplied constants out front. So watch this. I'm going to illustrate that for you. But in a way, I wouldn't do this if I was you. Well, what am I saying? Jesus, what am I saying? Look, I'm going to pull this 2 out front. If I pull the 2 out front, what's left in that integral? Yeah, you could say a 1, or just a dx, or a 1, right. All right, look, this is me, a teacher, illustrating these cool rules. You can really do these cool rules in your head. But I'm illustrating them for you, and here I go. Now finally I want to integrate. The truth is, I would have just integrated from the beginning. I would have done the power rule. X to the 5th divide by 5. Is that how you do it? X to the 5th divide by 5? With a 3 out front, I guess it's x to the 5th divide by 5, and there's a 3 out front. Anyway, you could do it there, or you could do it right here. This is it. Let's go over here. How do you do x squared? X cubed divide by 3. Is that how you do it? X cubed divide by 3. That's the new power rule. And then, oh, there's a 5 out front? Okay, there's a multiplied 5 out front. Hey, how do you do just a plain old x? Integrate an x. X squared divided by 2? I guess so. And this was a funny one. Maybe I needed to write a separate rule for this. Maybe you understand it. It is just a 1 while there's a 2 out front. But what is the antiderivative of a 1?
C.
X. The antiderivative of a 1 is x. Right. What's the derivative of x? 1. What's the antiderivative of 1? X. Okay, cool. So it's a 2x, negative 2x.
Oh, I see.
And then, on each of these little integrals, oh shit, I screwed up. Listen, on each of these little integrals, I could have put a little plus c, and then another little plus c, and then another little plus c, and another little plus c. But what do you do with a bunch of arbitrary c's? They're all arbitrary anyway, a C1, a C2, a C3, a C4. Well, why don't we just add them all together, put them into one big thing, and call it at the end, call it C. You with me? It's totally logical. Right. So there's really just one plus C. You don't need a bunch of individual plus C's. You understand? They're all arbitrary anyway. If you have a bunch of individual plus C's, just add them all together and call it plus C. So at the end, there is a plus C. And if I wanted to check this, I could do this derivative. If I do this derivative, where will I end up? Back in the integrand. That's called the thing you're integrating is the integrand. Yeah. His antiderivative is down here. His derivative is up here. Right. Right. Yes?
For the first integration problem, we just skip that step, right? Because it just divided out like evenly into 1.
What do you mean?
For the 3x cubed, like at the beginning.
Oh, So at the very beginning, I was doing some integrals, and I wasn't using the rule. I was using more instinct. Right.
Yeah.
When I first opened today, I was kind of thinking instinctually, and I didn't really use the rule. But now that we got the rule, I see what you're saying. Hang on a second. If I was trying to integrate a 3x squared, using the rule, we would add 1 to it. You get x cubed. You divide by 3. That's me doing this, and then there is a 3 out front. I better keep that 3 there, but now it cancels, of course. Right. That's what you're saying, I think. Yeah. So, right. Yes, you're right. So when I was doing this earlier today, I was just trying to get you to, what is his antiderivative without rules? But when you use rules, does it work? Yes, it works. Of course it should. All right, you guys, this is good stuff. These are the 3 main rules.
Do you leave the answer like that, or do you want it to be like in the
Well, okay, so this is my answer. I would leave it like that. I tell you what, I'll just give you this broad general statement here. When we do derivatives, all our first few months here, when we've been doing derivatives, have I always asked you to clean up your derivatives? That's been a big part of this class. Not only doing the derivative, but then cleaning it up. Guess what? With antiderivatives, I don't care so much about cleaning it up. I'm so happy if you got the dang answer. And also, it's just not as necessary for us to. So when we do antiderivatives, now if you're doing them and trying to check your answer in the back of the book, you may have to kind of do a little factoring. I mean, you might have to do some stuff that I'm not really requiring to see if you match the answer in the back of the book. But I don't require a big cleanup at the end of this. Now, I mean, there's not much to do. It's 3/5 x to the 5th. It's 5/3 x cubed. It's, I mean, somebody might suggest get a common denominator, but I'm not a fan of that. I don't want to do that. So this is perfectly fine. Perfectly fine, and I'm not interested in a big cleanup at the end of an integral. Here, what about this guy? Uh-oh. All right, I guess I put some stuff up here that ain't in your rules. Oops, sorry. No, that's okay. I mean, does that look like a hard problem? It looks like a big, long function. You mean you want me to find the antiderivative of that horrible long function? Well, yeah, I do. But one of the cool things you just learned is you really got 3 little individual antiderivatives here. You separate this by terms, and you do 3 little individual integrals is what you do. And do you know how to integrate a secant squared? It looks scary and complicated, but again, if you remember your trig derivatives, you might get lucky. Let's see, what's the derivative of tangent? The derivative of tangent is secant squared. So if someone says integrate secant squared, it's not hard, it's just memorized, it's just tangent. Are you with me? Secant squared isn't hard because he is a famous the derivative of tangent is secant squared, so the integral of secant squared is tangent. What are you going to do with the 2 that's sitting out front? Just keep it there, right? Kind of pull it out front and put it back. That's it. Nothing to it. How do I do this derivative? This is, antiderivative. See, even I'll misspeak. Be careful about my misspeaking. This is an antiderivative, please, of x to the 1/3, right, you guys? X to the 1/3. X to the 1/3. So how do you add 1 to it? X to the 4/3. Divide by 4/3, but instead of dividing by 4/3, I'm going to multiply by 3/4. That's it. This is e to the x. Do you know how to integrate e to the x? Really? You're right. That's everybody's favorite integral. Plus c. We're done, I think. We integrated him. We integrated him. We integrated him. We integrated. We found the antiderivative of this function. You know, I'm sitting here working on all these rules, and I'm very mechanical here. I haven't told you the big meaning yet of what we're doing here. But in math and physics and science and life, sometimes you know about the derivative and you're looking for the function. I mean, in real life, you kind of know about the rate of change or the derivative, but you don't know what the function is. So you work backwards like this. I mean, you try to find the function for a set of data maybe, and you might know about its derivative and how its slope works, so you can go back and do the antiderivative and find the function. I mean, there's a whole class called differential equations where you know about the derivatives and the second derivatives, but you don't know, and you're looking for the function. By the way, that's what it's a whole class. And not only is it one whole class, it's 2 or 3 or 4 classes. There's advanced differential equations, partial differential equations, advanced partial differential equations. I mean, there's a whole realm of mathematics that uses this. Yes?
How does x to the 1/3 become 3 over 4 x to the 4/3?
Well, I added 1 to it. So how do you add 1 to it? It's x to the 1/3. So I add 1 to it. Add 1. Add 1.
Oh, 4/3.
Yeah. And then divide by 4/3.
We'll just multiply by the reciprocal.
Yeah.
Right, I just didn't notice the whole +1 thing. I was just trying to see what you did.
Yep, that's it. I'm doing a power rule. I mean, you know, were all these things power rules? Of course not. This was not a power rule, but this was a trig rule. So hopefully I got my trig rules memorized. This was a power rule. This was not a power rule. This was a special exponential rule. You know, e to the x. By the way, I mean, so I could start writing down all these rules. I really kind of don't want to, but let's see. The integral of cosine, did we do that one today? The integral of cosine. What was the integral of cosine? Sine? What would be the integral of sine?
Negative cosine.
Negative cosine? I think it would. I just wrote down this one. I just kind of stumbled across this. What's the integral of secant squared? I mean, again, that's kind of a weird one to throw up here, but it's not weird. The reason this one's so easy is because he's a famous derivative, right? Listen, if somebody ever gave you this, what's the integral of secant cubed? Tell them to. Never mind. Just politely refuse. Chapter 8. You can learn this in chapter 8. It takes about a page and a half. I mean, it's a complicated, long procedure it's because secant cubed is just not somebody's famous antiderivative. So it's a very complicated, long procedure to figure this one out. And by the way, there's plenty of integrals you can't figure out. That's a new concept too. You know, with all our derivative rules, we can do with chain rules and product rules and quotient rules. Dude, we can do the derivative of almost anything nowadays. I mean, we're very accomplished. We, as a class, have learned all our derivative rules, and we can do derivatives. We can do the derivative of almost any crazy thing. But you can't. Some antiderivatives just don't exist. I mean, there's some problems you can just make up that don't have answers. They don't have an antiderivative. So there's plenty of things you just can't integrate. There's also plenty of things that is hard as hell to integrate. But then there's the easy ones, who are just somebody's antiderivative. And that's tangent x. If I wanted to keep, I guess there's 6 more here, or 3 more, right? If I wanted to keep going, what are they? If I wanted to, let's see. Oh, if I wanted to integrate a secant x, tangent x. Why is secant x, tangent x so easy? Because secant x, tangent x is the derivative of secant. You guys are supposed to memorize those damn things. What about a cosecant x, cotangent x? That was famous. That was cosecant. But it had a negative sign on it, and so since it doesn't have a negative sign on it, my answer has a negative sign on it. There's one more, cosecant squared. Cosecant squared was famous because that was the derivative of cotangent. Wait a minute. The derivative of cotangent was negative cosecant squared. So if I ask you to integrate cosecant squared, the answer is negative cotangent x. Look, these are my 6 derivative rules written backwards. I had 6 derivative rules for trig. And here they are written backwards. These are my 6 antiderivative rules for trig, for my basic trig functions. See, I don't even have one for this, you guys. Can you integrate a tangent? No, not yet. Later. And why not? Because tangent ain't somebody's famous, is not somebody's derivative. Well, he is somebody's derivative, but he's not famous. You don't know him. Why is secant squared so easy? Because you know him. Secant squared is somebody's famous derivative. He's the derivative of tangent. Therefore, the antiderivative of secant squared is tangent. But tangent is not somebody's famous derivative, so doing his antiderivative is a process that we'll get to later. So some stuff you just can't do. You just don't know. A lot of stuff. Let me think here. I taught you some basic power rules. I taught you these 6 basic trig rules. Here's everybody's favorite integral is this one. Ain't that everybody's favorite integral? Well, everybody. Maybe I should write it like this. Yes, this is everybody's favorite integral. Of course it is. And what's the answer? E to the x. It's just himself. Right. Wait a minute, there's one more. Can you remember, what else? If you were a teacher, what else would you think I need to include here? Remember this guy? What's the derivative of natural log? 1 over x. This is our derivative rule, right? From chapter 2, chapter 3. The derivative of natural log is 1 over x. So now, his associated antiderivative rule would be the integral of a 1 over x. What's the integral of a 1 over x? ln of x, the natural log of x. Technically, we put some absolute value on that x when we do this, because we can't have the input of a log function be negative. Of course, I might not. Yeah. Listen, this is an interesting one. And maybe, again, back to derivative rules. If you've got this derivative rule memorized, then it's easy to say, okay, yeah, I believe you, Mr. Smith, I believe you. Yeah, I got that derivative rule. Here's the antiderivative rule. But you might be thinking this. You might be thinking, hey, man, why don't you just do a power rule? A few minutes ago when I think I had a 1 over x cubed. What did I do for 1 over x cubed? I think I moved it up and called it x to the negative 3, and then I did a power rule. I add 1 to it, x to the negative 2, divide by negative 2. You guys with me? That's how you do it. That's how you do power rules, and that's how you do things that are in the denominator. You move them up and do a power rule, but not this one. You don't move them up and do a power rule. You don't. It's a log, and you're done. If you try it, you'll see why. Watch. Let's move them up and do a power rule. Okay, it's x to the negative 1. All right. Now what? Add 1 to it. If you add 1 to it, you get x to the 0. There's really nothing wrong with that, x to the 0, except now what am I supposed to do? Divide by 0. Well, there's major. You can't. Yeah, you go to jail. You can't divide by 0. That's the horrible thing. You cannot divide by 0, so this doesn't work. The power rule fails on x to the negative 1. The power rule fails. It doesn't work. It's got its own integration formula. It's the natural log function. The power rule works on everybody else. X to the negative 3 or x negative 2 or square root of x. You know, you move it up, you do a power rule, but not x to the first. X to the first is when it fails in the denominator. X to the first in the denominator is not a power rule, it's a log rule. Hey, I want to try one of these, and then I want to quit here, but one more problem. If I give you this, given f prime of x, yes, Carlos?
Over there where you have 1 over x and you have the x to the negative first, were you saying that it actually doesn't equal x to the 0 over 0? It's actually that natural log rule?
I'm sorry. Right. So 1 over x dx, if you tried to do a power rule, like I did, it fails because you're dividing by 0 is illegal. So this power rule fails right here. Never do this. Don't ever do that, right? That's why it has this rule, and the power rule fails, right? Look at this. This is a classic question. Given f prime of x is this, and f of 2 equals 4, find f of x. So this is kind of a classic question. It's a good homework question in your book. What are you guys thinking? What are you thinking? Well, first of all, they're asking you to find f of x, the function f of x. And what were you given? A derivative. So how do you get from a derivative to a function? How do you get from a derivative to a function? You do an antiderivative. You do an right? So I think I have to integrate 4x squared minus 2x. So that's what I have to do. You guys with me? Right. To get from a derivative to a function. So here I go. So how do you integrate? X cubed divided by 3. Can I call it 4/3 x cubed? That's how I talk. 4/3 x cubed. X cubed divided by 4/3 x cubed. What about this guy? X squared divided by 2. That's cool. When you divide by 2, it cancels. X squared divided by 2 cancels. Plus c. And this is my function. I mean, I just went from a derivative. I integrated a derivative. This was f prime, so this is f. So there's my function. Except, wait a minute, they gave me this. This is a piece of information that says when you have the function, when x is 2, the function value is 4. Or in other words, when x is 2, y is 4. What should I use? What should I do with that piece of information? Plug it in for x and y, and that will help me find a c. Yeah, then I can find c. Right. So when they ask me for this function, they're not asking, this won't be because of this nice piece of information, this piece of information helps me find c. And so this answer won't be a general family of functions. Well, right now it's a family of functions. But once I finish this question, it'll be a particular member of the family. It'll be the particular member of the family that goes through the point 2, 4. That's one way to say it. But here, at the end, we plug in a 4 for the y value. We plug in a 2 for the x value. That'll be 8. That'll be 32/3 minus a 4 plus c. And I can find c. I think I'll add this 4. That'll be 8. Then I got to subtract the 32/3. Okay, so that means 24/3. I think that's -8/3. It's a little quick fraction work, you guys, but I just found c. And so the answer to their question is f of x is, where's my f of x? Oh, right here. 4/3 x cubed minus x squared plus 8/3. Or I'm sorry. That c was a -8/3. I'm sorry. So I'm going to put minus 8/3. Sorry. You guys all right? Yes.
In the answer, you don't have the capital F.
You know, the way this was written, again, our notation sort of changes. I showed you that. What they gave me, they called it f prime. So what am I going to call his antiderivative?
No.
An f. Is it? Listen, it's weird. Now listen, but this goes back to the first 5 minutes of class. If they would have called this f, then I call his antiderivative capital F. See, because I kind of got no notation for that. But when they call him f prime, then I can say his antiderivative is f. You know, there's sort of this, maybe you think of it, I kind of think of it as this hierarchy. You got this function f, and we learned how to do derivatives. F prime, f double prime, and so on. And if you wanted to do an antiderivative of f double prime, where do you end up if you do an antiderivative of f double prime? At f prime. And if you do an antiderivative of f prime, you end up at f. But if you wanted to do an antiderivative of f, then we kind of run out of our notation, but we use this notation. I don't really have another notation. But, so this is kind of our hierarchy of, it just depends on how they talk in the problem or how they present the problem, what notation I try to use. Yes, Carlos?
When you said to find c and you had f2 equals 4,
Yeah.
were you saying that 2 is the value for x and 4 is the value for y?
Yes, sir. Yes.
But why is 4 the value for y?
Well, yes.